Okay, let's dive in. We're looking at something pretty fundamental to our daily lives, but maybe something we don't think about until, there's a pothole. We're talking about the future state of our roads.
And knowing what's coming is crucial.
Yeah, absolutely. Why should you care? Well, if you're anywhere near planning budgets or deciding which roads get fixed and when, predicting their condition is, well, it's vital.
It really is. Think about it. You wouldn't plan your household budget without knowing your likely expenses, right? It's the same for road agencies. Good predictions mean smart planning, efficient spending.
Exactly. But here's the tricky part, isn't it? How do we actually get a reliable forecast for our roads, especially if we don't have decades and decades of data piled up?
That's the core challenge, and that leads us straight into the research we're looking at today.
Right, a fascinating piece of research, actually. They took 3 different methods for predicting pavement conditions and basically put them in a head-to-head comparison.
Yeah, it's a really useful comparison. They looked at let's say, a traditional method and then 2 more complex modeling techniques. The goal was to see which gives the most accurate picture of road health over time.
So our mission for this deep dive is to figure out what this research tells us about which model works best. We've got the classic S-shaped curve,
The one most people might picture, yeah.
then something called the gray system model, or GM,
A bit less common in this field, maybe.
and Gaussian process regression, GPR. Sounds a bit more high-tech.
It's a machine learning approach, yes.
Okay, so we're going to break down the strengths and weaknesses of each based on this study. The idea is to give you the key insights, the takeaways, without you needing a PhD in statistics to follow along. Ready?
Absolutely. Let's start with that S-shaped model. It's kind of the baseline in a way.
Right. So imagine a new road starts off great, condition is high.
Right.
Then over time, wear and tear kick in, but slowly at first. That's the bottom curve of the S.
Gradual decline initially.
Then things accelerate. Traffic, weather, the deterioration speeds up. That's the steep middle part of the S shape.
Right. The main period of decay.
And finally, when the road is in pretty poor shape, the rate of getting even worse might slow down again. It kind of levels off at a low condition. That's the top part of the S.
And the researchers mentioned it's popular partly because it's relatively straightforward to grasp conceptually.
Simple is often appealing, but the research flags a pretty big limitation.
Yes, the data requirement. It generally needs a lot of data to be reliable.
How much is a lot?
Well, the rule of thumb they mention is needing a sample size. So data points, that's at least 10 times the number of parameters in the model.
Okay, parameters being like the settings that define that S shape. How fast it drops, where it levels off.
Exactly. So if your model has, say, 3 key parameters it needs to estimate, you ideally need data from 30 different road sections, or maybe 30 years of data for one section, something like that.
Okay. And that's where the problem comes in, right? For smaller agencies, maybe rural counties, or for specific, unique projects.
Precisely. They might just not have that kind of extensive historical data. So relying solely on an S-shaped model in those cases could be, well, risky.
And did the study's results bear that out?
Oh, definitely. It was quite striking, actually. In 3 out of the 4 scenarios, they tested different road types, different treatments. The S-shaped model gave predictions that were, let's just say, not very realistic.
Unrealistic how? What do they look like?
They predicted an almost flat line for the road's condition over time after repair.
Wait, flat. As in no deterioration.
Pretty much. It was essentially saying, okay, you fix the road, and then its condition barely changes for years.
Yeah.
Which, just doesn't happen in the real world.
No, roads definitely wear out. So that flat prediction is a huge red flag.
It really is. It signals that this model, at least in those situations with maybe limited data, just wasn't capturing the reality of pavement aging. If you relied on that, you'd seriously underestimate your future repair needs. Big budget problems down the line.
Okay, clear warning sign there for the S-shaped model. So if that one has issues, what about the alternatives? Let's talk about this gray system model, GM.
Right, the GM model. It's presented as an option that can actually work quite well even when you don't have tons of data.
How does it do that? What's the idea?
The basic concept is modeling systems where some information is unknown or uncertain, hence gray. It uses the limited observed data you do have to build a picture of the underlying trend.
So it works with incompleteness, in a way. The paper mentions they used a specific type, GM1, said tell us much.
Yeah, basically GM1 means it's a first-order model using one variable. So it's looking at the trend in just one stream of data here. That's the road condition rating over time to make its predictions. Relatively simple structure within the GM family.
And it sounds like this hasn't been used much for roads before.
Surprisingly little, according to the paper. They mention only one prior study that looked at it for a specific treatment called microsurfacing. So this research was kind of pushing it into a broader pavement context.
Interesting. Did they run into any technical hurdles using it? Something about a matrix being ill-conditioned. Sounds complicated.
It can be. Think of the math inside the model like building with Legos. An ill-conditioned matrix is like having wobbly bricks. The structure isn't stable, and small changes can make the whole thing fall apart or give weird results.
Okay.
This happened because some of their road condition data points were very similar or even the same from one year to the next. The model got confused.
So how did they fix the wobbly Legos?
Their solution was pretty neat. They added a tiny amount of random variation, what they called Gaussian noise, to the data points that were too similar, just enough to make them distinct mathematically, stabilizing the calculations, like adding a tiny bit of glue to the Legos.
Like giving the model just enough difference to work with. Makes sense. They also use something called a rolling horizon approach with GM. What's the benefit there?
Yeah, the rolling horizon. Imagine you're predicting tomorrow's weather. You'd probably look most closely at today's weather and maybe yesterday's, right? Not the weather from last month.
Sure, recent data feels more relevant.
Exactly. The rolling horizon does that for the road data. They use the most recent 4 years of condition data to predict the next year. Then, when the next year's data comes in, the 4-year window rolls forward and they make a new prediction.
So it keeps adapting to the latest trends.
Precisely. It makes the model more responsive to recent changes in how the pavement is behaving. Could be quite useful if, say, traffic patterns changed recently.
Okay, and one more tweak. A smoothing function. Why add that?
Ah, yes. That was to prevent something counterintuitive. Sometimes a purely mathematical model might predict that after you repair a road, its condition could actually improve slightly in the following years.
Which doesn't really happen, does it? Once it's fixed, it generally only goes downhill.
Right. So the smoothing function basically puts a brake on those unrealistic upward predictions. It forces the forecast to show either stability or decline after a repair, which aligns better with reality.
Got it. So with all these adjustments handling the similar data, the rolling window, the smoothing, how did GM stack up?
Pretty well, actually, especially for asphalt pavements.
Better than the S-curve.
Yes, definitely better than the S-curve in those cases. And for asphalt, it also outperformed the other advanced model, GPR, when looking at standard accuracy measures like MAPE and RMSE.
Okay, MAPE, RMSE, ways to measure prediction error.
Exactly. Lower numbers mean better accuracy. So the takeaway was that for asphalt roads, particularly when you might not have a massive data set, this modified GM approach looked like a really strong performer.
That's a significant finding. Okay, so S-curve has issues. GM looks promising for asphalt. What about the third contender? Gaussian process regression, GPR? Sounds like machine learning territory.
It is. GPR is a technique for machine learning, and the paper highlights its potential, again, especially with smaller data sets.
How does it work, in simple terms?
Well, it's described as non-parametric and Bayesian. Non-parametric means it doesn't assume the data follows a specific shape, like an S-curve. It's more flexible and learns the pattern directly from the data. Bayesian means it incorporates prior beliefs or information and updates them as it sees more data, giving a probability distribution for its predictions, not just a single number.
Okay, flexible and probabilistic. Any key advantages mentioned?
A big one is that it tends not to overfit the data. Overfitting is like tailoring a suit so perfectly to one person it fits nobody else. An overfitted model matches the training data perfectly but makes bad predictions on new data. GPR is generally better at avoiding that.
And this was also fairly new territory for pavement prediction.
Yes, the study notes is one of the first applications looking specifically at GPR for pavement conditions with limited sample sizes. So still exploring its capabilities here.
Did they face any challenges using GPR?
They did. One inherent feature of GPR, because it's so flexible, is that its predictions can sometimes fluctuate a bit from year to year, They might wiggle up and down slightly, even if the overall trend is downwards.
Which doesn't quite match how we think roads decay.
Yeah.
Usually it's a smoother decline.
Exactly. That year-to-year jumpiness isn't quite realistic for pavement deterioration.
So how do they address that? Another clever fix.
Seems so. They used an innovative approach by combining two different types of mathematical functions called kernels.
Kernels.
You can think of kernels, very broadly, as the tools GPR uses to measure how similar different data points are. By combining two specific types, a radial basis function kernel and a May-term kernel, they were able to encourage the model to capture that expected smooth, decreasing trend more effectively, reducing those unrealistic fluctuations.
Interesting. So blending the kernels helps smooth things out in the results. How did GPR perform after this adjustment?
It really shone for a specific type of pavement, composite pavements.
Composite, what's that?
That's typically asphalt laid over an older concrete base. For those roads, GPR came out as the best performing model across all the accuracy metrics they used: MAPE, RMSE, and another one called MAE.
Wow. Clear winner for composites.
Yeah.
And for regular asphalt.
It did well there too, often better than the S-shaped model, and sometimes, depending on which accuracy measure you looked at, it was competitive with or even slightly better than the GM model. So very strong performance overall, especially for composite roads.
Okay, let's pull this all together now. We've looked at S-curves, GM, and GPR. What are the big comparative takeaways from this research for someone trying to predict road conditions?
Well, the clearest message, I think, is that both of the more advanced models, GM and GPR, generally did a better job than the traditional S-shaped model in this study,
That S-curve just couldn't handle it, realistically, in most cases.
especially with its tendency to predict that flat deterioration rate. That really seemed to be its Achilles heel here. So the first takeaway for you is be cautious about relying only on that simple S-curves, particularly if your data isn't vast.
Makes sense. What about the practical side of using GM versus GPR? Are they equally easy or hard to use?
Good question. There's definitely a difference. The S-shaped model, for all its predictive flaws here, is the easiest to implement. You could probably do it in a spreadsheet.
Okay.
But GM and GPR, they typically require more specialized software. The paper mentions MATLAB, Python. So you need some technical expertise or access to it to actually run these models.
Right, so there's a trade-off. Simplicity of the S-curve versus the potentially higher accuracy but higher technical demand of GM and GPR.
Exactly that. Ease of use versus predictive power.
And the research also hinted at slightly different strengths between GM and GPR themselves, GM being maybe better at sudden changes.
Yes, that rolling horizon approach used with the GM makes it quite sensitive to the most recent data. So if there's an abrupt change in conditions, maybe due to a harsh winter or a sudden increase in heavy truck traffic, GM might pick up on that shift more quickly.
And GPR, its strength was particularly...
For those composite pavements, its flexibility seems really well suited to modeling the potentially more complex behavior of that layered structure. And it provided generally smooth, reliable predictions once they combined those kernels.
So, if you're listening and you want that quick, solid understanding, what's the core message?
I'd say it's that moving beyond the simplest models can really pay off. This research shows there are more sophisticated tools like GM and GPR that can offer a more reliable glimpse into the future of our roads, especially when data is scarce or for certain pavement types.
It's like having sharper tools in the toolbox for infrastructure management.
Precisely. And understanding that these better tools exist, even if you're not the one running the models, is valuable. It helps you ask the right questions, maybe push for better forecasting methods within your organization. It leads to smarter planning, better use of taxpayer money.
Absolutely. Okay, so wrapping up the key aha moments then.
Yeah.
First, the classic S-shaped models.
Yeah.
Maybe not as reliable as we thought, especially with limited data.
Definitely showed limitations here.
Second, the gray system model, GM. Looks like a really promising approach, particularly for asphalt roads when data is maybe a bit thin on the ground.
Yes. Strong contender for asphalt.
And third, Gaussian process regression, GPR. A powerful machine learning tool that really excelled, especially for predicting the future of those composite pavements.
Clear winner there, yes.
So this all leads to a final thought, maybe a challenge for you listening. Given these findings,
How should this change things?
exactly, how might transport agencies, planners, engineers, how might they need to rethink their approach not just to modeling, but maybe even to data collection itself.
That's a great point. If these advanced models offer better predictions but maybe work best with certain kinds of data, what should agencies focus on collecting?
Right. Is it just about condition scores?
Hmm.
Or do we need more detail? Maybe more frequent measurements, data on traffic loads, truck percentages, specific weather impacts, the actual materials used.
Could be. Perhaps feeding richer data into these more sophisticated models is the key to unlocking even more accurate predictions down the line. It's something to really ponder what data becomes most valuable in this new modeling landscape.
A fascinating question for the future of road management.
Indeed. Better data plus better models could really lead to more proactive, cost-effective maintenance. Smoother roads for everyone, hopefully.
Well, there you have it, our deep dive into predicting the future of pavement. We hope this gave you a clear, useful overview of this important research.
And if you are curious, you could certainly look up terms like gray system theory or Gaussian process regression for more technical detail.
But hopefully you've grasped the core insights without needing to wade through the equations. Thanks for joining us on this exploration.